Like to thank the organizers for the kind invitation and also for all the work they have done so that we can meet here at this wonderful place. You see the title here, and the results which I'm going to present stem from joint work with Wolfgang Schmidt and Jinghai Zong. Both are in the audience here. And the main concept I'm talking about are zero-sum sequences over finite abelian groups. So let's briefly put together the basics. I'm sure you know all about it. So we fix a finite abelian group, additively written, an arbitrary subset. And by a sequence, we always mean a finite sequence of terms. We do not consider their order, and we allow repetition. And well, we say it has sum 0 if the elements sum up to the 0 element of the group. And of course, all the sequences, you can define an operation, you simply glue them together, then you have a semigroup or a monoid. Of course, this is commutative, and the same is true for the zero-sum sequences. And the main motivation of what I'm going to do stems from algebra, so it's very convenient, but this is not an essential point to consider the sequences as elements of the free abelian group, and then BG0 is a submonoid as you see it here. So what is a minimal zero-sum sequence? If the elements of the sequence sum to 0 and no proper subsum is equal to 0, and these are of course the irreducible elements of the semigroup. Well, so we have a semigroup. Suppose you have an arbitrary semigroup, commutative or not. And when you have an element, suppose you can decompose it, you can factorize it into atoms, into irreducible elements, then the number of the factors is called the length of the factorization. And L of A gathers all the possible factorization lengths. So this is a subset of the positive integers, and we can put them all together, then we get a whole family, a family of sets LA over all elements. And this system is a most studied invariant in factorization theory, which describes the non-uniqueness of factorizations. And our topic here, so we take the semigroup, we take the monoid of the zero-sum sequences over our given abelian group, and we study the family of sets of length. Maybe you ask, okay, well, why we are doing this? This is an artificial topic. No, it is not. There's a lot of motivation behind, and let me start with an example going back to the 70s and given by Narkiewicz in the late 70s. Consider a ring of integers R. This is a Dedekind domain, and in a Dedekind domain, every ideal is a product of prime ideals. So we look at the map, sending elements to the principal ideals, and whenever we have an ideal, we look at its prime ideal decomposition and map it to the sequence of ideal classes. And by definition of the ideal class group of the domain, this ideal is a principal ideal if and only if the sequence is a zero-sum sequence. And if you look at this again, you figure out that for every ring element A, the set of lengths of A with respect to the domain R is the same as the set of length of the zero-sum sequence beta A with respect to the semigroup B of G. This is just the definition. And so why we are studying LB of G, we study LB of G because this is a system of set of lengths of the integers. So this was first formalized in the late 70s by Narkiewicz, and in the meantime there is much, much more. So L of BG has a real strong universal character. What I showed you here does not only work for rings of integers, it works much more general for commutative Krull monoids. Commutative Krull monoids include all Krull domains. They include all integrally closed Noetherian domains. And this runs more or less for free. But there's also some very recent development. This L of G is also a set of lengths of certain non-commutative Dedekind domains which pop up as maximal orders over central simple algebras. And also, if you take a ring of integers, this is a principal order. Also for certain non-principal orders which are close, if you take a non-principal orders which are close enough to the ring of integers in a number field, you have the same phenomenon. So there's pretty much motivation behind why we study L of G. Okay, but I will use a basic example for algebraic number theory to explain the problems I'm going to look at. Okay, so let's go back more than a century. So if we have a ring of integers, then by the definition of the class group, the ring is factorial. It's a unique factorization domain, if and only if the class group is trivial. And it's classical philosophy that the class group determines the arithmetic, determines the non-uniqueness of factorizations. It was more than half a century later when it was observed by Karlitz that let us look at sets of length. Let's look at all equations of this type. Then there might be non-uniqueness, but at least the number of factors is always the same. This happens if and only if the class group has at most 2 elements. And it was also started in the 1970s when Narkiewicz asked, is there a sort of inverse relationship? So do arithmetical phenomena, do phenomena of non-uniqueness of factorizations give us back the class group? And there are many answers to this. The proofs are not, there are many answers of this starting from the 80s, but here the question of course is what properties should we take for the characterization? How natural are these properties? So there are positive answers, but people in this area think that the first answers, the properties have a certain artificial flavor. The main invariants of factorizations which have been studied are sets of length and all what comes with them. Yeah? So the question occurred very recently, very naturally, whether or not families of sets of lengths are characteristic for the group. Yeah? Suppose take 2 finite abelian groups, you might think of them of class groups from Dedekind domains. If the families coincide, what about the groups? And okay, so what is L of G? This is a family of sets of lengths from a certain monoid. Yeah? The monoid are the monoid of zero-sum sequences. So this question only makes sense if a necessary condition for this is given two groups, any 2 groups, then the monoids of zero-sum sequences are isomorphic if and only if the groups are isomorphic. Of course, this fact is a necessary condition if we are looking for a positive answer here. Let's start with a couple of examples. Yeah? Suppose we have a trivial group. How do these zero-sum sequences look like? It just takes a 0 element and repeat it over and over. How do sets of lengths look like? They are all singletons, of course. Let's take a group of 2 elements. How do the zero-sum sequences look like? Well, I can repeat the 0 element k times, and the non-trivial element I have to repeat it an even number of times. The system of sets of lengths still has this form. Now suppose we have at least 3 elements, and suppose we have an equation of this type, that k minimal zero-sum sequences may be written as a product of L minimal zero-sum sequences. Let's look at any power. Of course, we can arrange distinct factorizations here. So we see that the m-fold subset is contained here. So as soon as we have a set of length which is non-trivial, we immediately get arbitrarily long sets of length. Further simple property, of course, if we take a zero-sum sequence A and glue together the zero element 0y times, we get all shifts. Let's consider a final, still very trivial example. Let's look at the cyclic group with 3 elements. What are the minimal zero-sum sequences? Well, I can take the element G, repeated 3 times. I can take minus G, repeated 3 times. And I can take the minimal zero-sum sequence consisting of minus G and G. Of course, U and minus U can be written as phi times phi times phi. If I do this k times, I get an interval, and we get all shifts. So for a very simple group, you can write down in an easy way as an exercise the full system. And if you do it for this group, you will figure out immediately that this is the same. Here's the main result. Suppose you have two groups, G and G. You have 2 groups, G and G prime, whose families of sets of lengths coincide. And suppose we are away from this trivial example. The groups are larger than this. If this happens, and if one group, G, is either cyclic or if it is a rank 2 group, then G and G prime are isomorphic. The same is true for elementary 2 groups, which is easy to show, and the same is true if G has this form R copies of Cn, where R is small, and again, trivial cases are excluded. And since we have this exceptional behavior of small groups, it could make sense to check small groups, but apart from the groups we had, small groups are also characteristic up to Davenport constant 11. Well, so this is the main result, and I would like to discuss 2 ingredients how to prove this type of results. And the first deals with short set of lengths, and the second ingredient comes from long sets of lengths. Let us go to short sets of length. Okay. I already mentioned it, but here still is the formal definition of a Davenport constant. I'm sure most of you are familiar with it. So what is a Davenport constant? It is the maximal length of a minimal zero-sum sequence. Or in other words, it's the smallest integer L. Whenever you have a sequence consisting of at least L terms, you find a non-trivial zero-sum subsequence. This is a well-studied invariant since the 1960s. If our finite abelian group has this structure, the canonical form, look at this invariant D star 1 plus Ni minus 1 over the group invariants. And then it also goes back to the 60s that we have equality here for P groups, for cyclic groups, for rank 2 groups, and for certain other families, but we do not have equality in general, yeah? There is recent work on the Davenport constant. Here you see a number of people, colleagues who have worked on it in recent years, but the state of the art is far away to get a precise formula for the Davenport constant. The question is still open whether we have equality here for rank 3 group. It is open whether equality holds for groups of the form Cn to the power of R. Okay, so let's try to do some factorizations. Okay, so let's take 2 minimal zero-sum sequences, U1 and U2. Let's try to regroup them, to redecompose them. What do we have to do? Okay, suppose U1 consists of S elements, U2 of T elements, and we recombine this to minimal zero-sum sequences. Okay, let's suppose the 0 element pops up nowhere. If U1 is equal to 0, then L is 2. How many elements do we have to the left? So S is bounded by the Davenport constant. T is bounded by the Davenport constant. So we have at most 2 times Davenport constant on the left group elements here. If you want to recombine them, every zero-sum sequence has at least 2 elements. So we have at most, so L is at most dg. And of course, if U2 is just the negative of U1, if H1 is minus G1, H2 is minus G2, then we get dg here. So if we ask, let's start with k elements on the left, how large can L be? And we call this rho k, how large can L be? Then rho 2 is a Davenport constant. And the same argument is true for all even numbers. So we have a classical combinatorial description of this arithmetical invariant. And again, by a counting argument, if the number is odd, if you have an odd number here, then the rho 2k plus 1 is between these 2 upper bounds, yeah? Between the upper bound and this lower bound. Here's a further observation. Take 2 groups, G and G prime. If their systems coincide, the rho 2 values must coincide. But the rho 2 values are simply the Davenport constants. So if this holds, the Davenport constant must be the same. Now, let us fix one group G. There are only finitely many G prime, where the Davenport constant of G prime is a given fixed value. So therefore, there are at most finitely many groups up to isomorphism such as this can be true. Okay, at least we have this. Well, and you see, if we really want to work on this, we need to know, we need information on the Davenport constant, but we would need more. We would like to know about how do minimal zero-sum sequences look like, yeah? We need inverse results on the structure of minimal zero-sum sequences. And there's this result by Savkiev and Jen. It gives a strong structural description of long minimal zero-sum sequences over cyclic groups, yeah? If you have a cyclic group, of course, every minimal zero-sum sequences can be written down for one fixed generator G, and the result states there is a G such that the ni's sum up to n. If you know this, you have this structural result, you can show that for cyclic groups, the rho 2k plus 1, the rho 2k plus 1 equals the lower bound. And the ingredient is a structural result on minimal zero-sum sequences. Suppose the group is non-cyclic. If the group is non-cyclic, and suppose you are in a group, the results are more general, but let's restrict to this situation, yeah? If the group is, this is has not been written down, now the groups are non-cyclic, yeah? Then there is a k star. From a certain point on, the rho 2k plus 1 value equals the upper bound. In many cases, the k star is equal to 1. If we have a rank 2 group, the k star is only 1 in a very limited number of cases. So you see here, non-cyclic groups and cyclic groups behave in a very different way. And this is almost the proof of the characterization in case of cyclic groups. If you want to, suppose you want to prove a characterization result for rank 2 groups, the main ingredient is a recent structural characterization for minimal zero-sum sequences of maximal lengths in rank 2 groups, yeah? Don't read the whole statement, just what is written down here. If we have a rank 2 group and a minimal zero-sum sequence of maximal lengths, the structure is completely determined. This has been done by several authors. The prime number case was settled by Christian Reyer. Multiplicity results to the group Cn by Cn were done by Gao, David Krynkiewicz, and myself, and the general case has been finished by Wolfgang Schmidt. And this is a main ingredient in order to prove the characterization result for rank 2 groups. let us go to long sets of length. Sets of length have a well-determined structure. Yeah? We already know sets of length over finite abelian groups having at least 3 elements. They are long, and they are a sort of arithmetical progressions. Whereas one universal bound, every set of lengths is an arithmetical progression with this bound. Okay, what is an AAMP? Let us fix a difference D. So an almost multi-progression is a union of arithmetical progressions with the same difference D and with a variety of different starting values. So look at the L star. L star is the long central part. Everything is shifted so that we start with a 0 element here. And L star is an arithmetical progression with difference D, and we have several starting points, yeah? Up to the very end. And at the beginning and at the end part, we may have some gaps, but everything is contained here. And this structural description is best possible in a sense proved by Wolfgang Schmidt. So given any M and any finite set delta, there is a group G, one fixed group G, such that any AAMP with these parameters occurs in L of G. Did not tell you yet what the delta star is, and I'm not going to do so. You see a definition here, but delta star will be the topic of the next talk. So I don't talk about this delta star. But let me just end with 2 examples. So in order, a crucial ingredient to do the characterization work is to study the possible periods, is to study these sets D, which actually can pop up. And I end with 2 examples. Okay, we want to solve the characterization problem for rank 2 groups. So suppose one group has this form, and you have a group G prime, and the families of sets of lengths coincide. If you want to show that the groups are isomorphic, you have to write down sets of length which pop up here and do not pop up somewhere else. This is a job you have to do. And here's a set of lengths which does the job. Let's look at this set of lengths. How does it look like? This is a shift element. Let's forget it for the moment. This is one extra element. Let us forget about it. So what is LK? So this is an arithmetical progression with difference n2 minus 2. This is this n2. It's an arithmetical progression with this difference. And we have these starting values. So the D in the abstract setting now consists of these 3 values, and the small d is the n2 minus 2. So I'm pretty sure that every one of you needs maybe half an hour or an hour to figure out that these sets are really sets of lengths over this group. But of course this is not enough. No? What is really needed is an inverse result. Suppose you have a group, and you omit some extremal cases. You have a group with this exponent and a given Davenport constant, and if you suppose that the sets before pop up as sets of length, then you can show it is really this group or several other extremal cases which have to be excluded in a different way. Yeah? So these sets, LK, let's have a look at them again, with these period D and the difference n2 minus 2, they do not only pop up here, but they are more or less characteristic. And combining these ways, so say a study of short sets of lengths, a study of the row K, and a study of these periods, these are the main ingredients for to prove the characterization result in rank 2 groups. And let me end with drawing your attention to a forthcoming conference in Graz. It will be in the first week of January, And many of you know about it and have already registered for it. Thank you. So let me remind you of it, and the registration is still open. We would be happy to welcome all of you in Graz. Thank you.